Hello, my name is Christopher Guevara. I'm a mechanical engineering student at the University of Louisiana at Lafayette. This is the final 10-minute update on my summer ORU project, Yield Strength Prediction of High Entropy Alloys Using Machine Learning for Rapid Alloy Design. I would like to thank my sponsors, the Texas A&M RU program, and the Department of Energy and the National Nuclear Security Administration, award number DENA 003857, as well as my graduate mentor, Brent Vela, and the principal investigator, Dr. Raimundo Arroyave. High entropy alloys are vital to the further development of the gas turbine engine. These engines have relied on nickel-based superalloys because of their high temperature applications and favorable high temperature properties, such as resistance to static loading, fatigue, and creep conditions. However, these nickel-based superalloys cannot keep up with the increased temperatures needed to improve the engine's efficiency. In order to enhance modern turbine technology, new novel alloys must be developed. High entropy alloys have mechanical properties similar to that of the traditional nickel-based alloys and consist of four or more elements alloyed at different concentrations. For this project, the HEA alloys must be ductile at room temperature and possess a high yield strength at high temperatures. And currently, there is no cost-efficient method to predict the yield strengths of these theoretical HEAs. The first step of our research plan was to create a database of the mechanical properties of the high entropy alloys. This was done by creating a Python script in order to query citronation, an artificial intelligence powered materials data platform, which returned a database of HEAs and their properties. This data was then featurized with stoichiometric averaging, thermo-calfad calculations, and MapMiner feature engineering. The research plan summarized in this flowchart was followed utilizing many different machine learning regression models. Although, even our best performing regressor, the extra trees regressor, did not have an R-squared value greater than 0.7. The preliminary results shown here for the extra trees and the gradient boosting regressor performed decently with an R-squared of 0.55 and 0.44 respectively. This is considering no feature selection was used, no hyperparameters were tuned, and the composition space was not narrowed, which are all methods we can use to improve the performance of these models. These are the next two models that performed pretty well, with the support vector regressor at an R-squared of 0.4 and the random forest regressor at an R-squared of 0.49. These four regressors were then improved by the methods I just mentioned. In order to improve the accuracy of the four regression models just shown, the composition space was analyzed. This bar chart was created to show the distribution of elements in our dataset. Our primary interest for this project is on BCC RHEAs, or reflective high entropy alloys. It is also important to note that this well-known FCC Cantor alloy, cobalt, chromium, iron, manganese, nickel, is highly represented in our data and may be an alloy of interest in future work. Here, the elemental distribution was broken up based on microstructure so that we could focus only on BCC alloys. An FCC alloy graph was also created and may be utilized in future research should the BCC systems fail to produce a working model. Hafnium, molybdenum, niobium, tantalum, titanium, vanadium, zirconium are all highly represented in the BCC alloy space, so we chose these elements to further narrow the compositional space. Another step in analyzing the alloy space was to look at what alloy systems were present. The systems were again split into two graphs based on microstructure. The first three systems in the BCC graph are of particular interest to us in this project. Next, we readdress the question, why do we need a yield strength regressor for alloy design? And the answer was that it is needed to predict which regions of the HEA alloy compositional space may contain alloys that have exceptional yield strength. The next question we addressed was, do we need to predict the exact yield strength values, or will an accurate prediction within a set range suffice? And the answer to this was, an accurate prediction of yield strength is ideal, but given our lack of success with the regressors, a classifier could be used to act as a filter to identify alloys that are likely to have a high yield strength. However, classifiers cannot easily be used for optimization schemes, which means that while a classifier could determine whether an alloy system is above or below a certain yield strength, it cannot determine which of those systems had the highest yield strength. Due to data limitations and time constraints, we decided to forego the regressor approach and reframe the problem as a classification problem. The question we built our classifier around was this: is the yield strength greater or less than 400 megapascals at 25 degrees Celsius? The classifier was also not limited to the alloy space chosen earlier for the regressor models, and this is because classifiers work better with a large design space. The data was featurized automatically using Auto Map Miner, and we ended up with 152 features for each alloy system. Some of the added features are associated with valence orbitals, electronegativities, compositions, and other thermodynamic properties. Feature selection was then done using mutual information. The bar graph shown demonstrates the feature importance of the top 14 features, and the best performing model utilized 112 of the 152 available features. The best performing classifier was the random forest, and it had a cross-validation receiver operating characteristic area under the curve score of 0.89. This isn't a perfect score, but the random forest classifier is still able to pretty accurately predict yield strength over a large compositional space. It is also important to note that through principal component analysis, it was shown that the first two features do not capture all of the variance in the dataset. In conclusion, while the regressor models failed to meet our specifications, primarily due to a lack of data, a classifier was successfully built that can predict whether a reflective high-entropy alloy will have a yield strength above 400 megapascals at 25 Celsius. This classifier can be modified to be a regressor whenever more experimental data becomes available. HEAs and RHEAs are still relatively new and unexplored, so there is a limited amount of data until more research is conducted. The frameworks that were created in this project will be of great use when more data becomes available. I would again like to thank my sponsors and my mentor, Brent Vela and Dr. Raimundo Arroyave, as well as everyone that played a part in making this OREU such an exciting and rewarding experience.